In a previous video, we drew these molecules and we said that these two are mirror images, so they are enantiomers. These two, for example, they are not mirror image, so they will be diastereomers. Also, let's remember the convention for Fisher projections is all the vertical lines will be the stashes and the horizontals will be wedges. And then when you are looking at the absolute configuration of the chiral centers, always in the enantiomers you need to have the configuration of the enantiomer will be the opposite and at all chiral centers. And we did the absolute configuration for these molecules and say, for example, this center, priority 1 is the OH, then we said priority 2 is the aldehyde group. So we go, say, 1, 2, and then 3 below, and that was 4. So we said the configuration here is, looks like is, it is R, because we're looking at this molecule with the hydrogen pointing outwards, right, on the wedge. Doing the same for the carbon below, we say priority 1, and then of the two carbon chains we established before that the substituent above has attached an oxygen and then a carbon hydrogen, so it will be the second priority. So for the, I'm going to use a, say a different color because I don't want to overlap with that. So that's a tricky part. So that was for the carbon above, and for the carbon below, I am going to say then the priority 1 is this oxygen. This one I'm using a different color. Priority 2 is a chain above. Priority 3 is the chain below, and priority 4 is this. So I'm going to go 1, 2, and 3. It also looks like S, but since you're looking at that with the hydrogen pointing towards you, it will be R. We also determined that the configuration at the enantiomer is inverted. So the two chiral centers will have the opposite configuration. So if this is R, this will be S, and this is R, this also will be S. And so another thing that is important here to note is that actually these molecules have a plane of symmetry. Let's imagine that I have a mirror here. Now, cutting the molecule in half. Well, actually, no, sorry, doesn't have a plane of symmetry because this is different than that. I need another example. So I'm going to remove that one. That's not. So, but if I'm going to draw another example in another video. So, it's not, that was not a good example. So let's talk about what happened with the configuration of the other molecule. And we said that the relationship between this and that is not enantiomers. We see that here, they don't look mirror image, right? And so if we look at the absolute configuration now of the carbons, notice that this one right here is identical to this one. So this is R as well. So identical this and that. Top carbon, so that's R. Now the one here in the bottom is actually like this one. So S, S. So notice that now for the enantiomers, the two centers were here R, and here is S. So the two centers are inverted, and in the case of the diastereomers, only one center. If you see this two, the carbon above is inverted, but the carbon below is not. So that's another way to distinguish diastereomers. Again, the enantiomers will have all the chiral centers if there's multiple inverted, and not the case for diastereomers. And one more thing I wanted to show in this video is what I was trying to do in I'm gonna change this molecule just a little bit, because now what I want to do is I am going to there's something similar, but not quite the same. So I'm gonna now change the substituent below, and I'm gonna say here that I have another aldehyde. Right, so I need to check the absolute configurations though. Let's see if that's still S. So we'll see what happens here. So highest priority is oxygen, but now the second highest is this. So with S, this is actually R. Because I changed the substituent, the configuration, you need to check. It might change. So in that case, again, first priority, second highest priority, and then third. So you will go 1, 2, 3. It looks like S, but since you're looking with the hydrogen pointing towards you, this is R. Now let's draw another molecule. In this time, this is the RR. And I'm going to draw another molecule that would look similar to this. Let's see, I want to do this bolder. Yes. So the carbon in the top, I am going to draw identical. Remember, this is your aldehyde group. And now the carbon in the bottom is going to be different relative to that, the absolute configuration. This is CHO, so an aldehyde. Now, what we're looking at here is at a molecule that if you see this, we have a plane of symmetry. So now, in other words, if you put a mirror here in the middle, you will see that OH mirrors the OH, H mirrors H, and aldehyde, aldehyde. So that's something that we learned in other videos with different projections, but here we identify this as a meso compound. Now, looking at the absolute configuration, notice that the top carbon will be the same because, again, we haven't changed the substituents. However, here we see that the OH and the H have now exchanged places. So if this is R, this should be S. And now, these two are not related as mirror image, so they are diastereomers. Diastereomers. And notice that the configuration at the top carbon is the same, but at the bottom is not. To be an enantiomer, they would need to have both centers inverted configurations. Here we have inverted, this is not. Okay, another way to say that. So, but again, we notice that they're not mirror image. That's immediately you identify that as diastereomers. And remember that if we have a molecule like this with a plane of symmetry, and this is in the Fisher projections, but there you can see that also in Newman and the wedges and dashes. But having that plane of symmetry identified that as a meso compound.